Hello, so the frequency response is a steady-state response of a system to a sinusoidal input. Our objective is to vary the frequency of the input signal over a certain range and study the resulting response. This lecture will be a continuation of the last lecture I posted on the root locus, as they both complement each other. This is the most powerful tool in convention control theory. The Nyquist stability criterion, which we later discussed, enables us to do an absolute and relative stability of linear closed-loop systems from the knowledge only of their open-loop frequency response characteristics. An advantage of this approach is that it's simple and can be made accurately. We can design a system where the undesirable noise is neglected. When designing, we adjust the frequency response characteristics of the open loop transfer function by using several design criteria to obtain acceptable transient response characteristics. So it is important to obtain the steady-state outputs to the sinusoidal inputs. We denote the input by x of t and the output by y of t. The output will be a sinusoidal signal as well of the same frequency with different magnitude and phase angle. The frequency response can be calculated when replacing s with jw, and m is the amplitude ratio or magnitude, and this is theta is a phase shift between the input and output. In the frequency response, we vary w until the entire frequency range of interest is covered. After derivation, we reach this y of a steady state of t, where a is a constant and a bar is the complex conjugate of a. Here we can see in this graph that the input and output have the same frequencies but different magnitude, and there is a phase shift between them. This is how we calculate the amplitude ratio, and this is how we calculate the phase shift. Also, the steady state response characteristics can be calculated from the sinusoidal transfer function. Three commonly used representations of the sinusoidal transfer function will be discussed later on, including the Bode diagram, Nyquist plot, and the Nicholas plot. Now we will begin with Bode diagram. It consists of two plots over each other, the first one being logarithmic magnitude in dB, and the second one being the phase angle or shift versus the frequency. The advantage of this is that we can analyze the characteristics at low frequencies as well. We have four basic factors that occur in the usual transfer function, and knowing all of them, we can construct the complete log plot. The first one is like gain k, where the log magnitude is a horizontal straight line at 20 log k decibels per decade, with a phase angle at 0. The second factor is the integral and derivative factors, which one has a slope of minus 20 dB per decade, and the other has a slope of 20 dB per decade with no corner frequency, and they cross the magnitude line at 1, 0. The third factor is the first order factors, where the slope is 0 from 0 to the corner frequency, and the slope becomes plus or minus 20 dB per decade depending on this value here, when it's going from the corner frequency to infinity. This is the value of the corner frequency, and this is the value of the phase. And the fourth factor is the quadratic factors, where this is the magnitude, this is the resonance frequency if depending on damping ratio, this is the phase, and this is the corner frequency as well. And the same goes like for the third factor as for the slope, except for when it goes from the corner frequency to infinity, it's plus or minus 40 dB decades instead. And also the value of the damping ratio determines the shape of the curve for this case. To better understand how to plot each factor, I've constructed these diagrams right here. For the gain factor, we can see it as a zero slope. For the integral and derivative factor, we can see how much each slope is, previously discussed, and it crosses the magnitude line at 1, 0 for both. The first order factor for either a minus 20 dB per decade slope or a plus 20 dB per decade slope. And this is the quadratic factor for a specific case of damping ratio of 0.7. We can see from the 0 till the 1 over t corner frequency, it is constant at 0. And then for after that, as it tends to infinity, it has a minus 40 dB per decade slope. Next, for a minimum and non-minimum phase system, we should know the transfer function is dependent on the poles and the zeros. G1 is a minimum phase system where there are no poles or zeros in the S-plane, while G2 is a non-minimum phase system where there is a lag due to the poles and zeros in the right-hand system. There's a non-minimum phase element, which is why the G2 looks like this, and the G1 looks like this. For experimentally determining transfer function using Bode plot techniques, we first determine the damping ratio by measuring the resonant peak near the corner frequency of the quadratic form. Then we determine the gain from the low frequency portion. We need to find the type of system where there's a type 0, type 1, type 2, and each have their own requirements. Next, for the Nyquist plot, we plot the transfer function along the real and imaginary axis. where each point on the curve is for a specific frequency. The advantage of using this form of a polar plot is it shows the frequency response characteristics of the system over the entire frequency range in one plot, and each form has a different form on the polar plot. Some examples of polar plots are as follows. We can see that each frequency point has a different point on the curve. There are some other forms of polar plots for the Nyquist. For example, this is for the quadratic form. Next, we have this Nyquist stability criterion, which is z equal n plus p, where z is the number of zeros in the right-hand side of the S-plane, n is the number of clockwise encirclements of the minus 1 plus 0 j, and p is the number of poles in the right-hand side of the S-plane. We are able to determine if the system is stable from the value of each variable. For example, if n equals zeros and there is no poles in the right-hand side of the plane, then the system is stable. If n is greater than 0, then the system is automatically unstable, and there are different cases in our textbook as well. The final form of the polar plot or type is the nucleus plot, where we plot the logarithmic magnitude in decibels, which is the phase angle for that range of frequency. So it's like a combination of the two Bode diagram plots. The gain and phase margin is used as a measure of the margin of stability. The gain margin is calculated as such, kg, and the phase margin as such. The gain crossover frequency is a frequency when the magnitude of the open loop transfer function is equal to 1, and the phase crossover frequency is when the phase angle of the open loop transfer function is equal to minus 180 degrees. There are also different indications of stability for the frequency of the system with respect to the gain crossover frequency from the information obtained from the open loop frequency response. Now, for a lead compensator, it is used to improve the transient response characteristics of a system, and it acts as a high-pass filter. These are the following steps for designing it. First, we define the new k and the new transfer function. Then we find the gain k that satisfies the given static character. We do Bode diagram, find the phase, lead, angle required, the new crossover frequency, the attenuation factor, alpha, the kc, and then we check the gain margin. And if it doesn't satisfy, then we repeat. For the lag compensator, it is used to improve the steady-state error and characteristics and act as a low-pass filter. The design of it as follows. You first define k and the new transfer function. You find k for that static error. You find the new gain crossover frequency if needed. And then you find the t from the corner frequency, the attenuation factor beta, and then finally the kc required. Finally, we have the lag lead compensator, which is used when you want to combine the effects of the lag and lead compensators. The steps are relatively easy to follow in the book once you understand the other two compensators. We have now gone over the Bode diagram, polar plots, as well as the different compensator designs. You should now be able to understand design by the frequency response method through our textbook without a problem. Thank you.